Everything you've seen in sci-fi about warp speed is wrong. Not because faster-than-light travel is impossible, but because the real physics is stranger and, honestly, way cooler than fiction ever imagined. In 1994, a physicist did something nobody expected. He found a legal loophole in Einstein's own equations, a way to move faster than light, without technically moving at all. Today, I'm going to show you exactly how the Alcubierre Drive works, the real math, the real problem, and why NASA is quietly taking it seriously. If you've ever watched Star Trek, you've seen a warp drive. But here's the twist. In 1994, Mexican physicist Miguel Alcubierre proved that something like it could actually work under general relativity, Einstein's own theory of gravity. The catch? It requires a form of matter we've never seen, energy we can barely produce, and it comes with a side effect that could vaporize anything waiting at the destination. Let's break it down properly this time. Here's the concept that changes everything. In Alcubierre's model, the ship never moves. Not even a little. Instead, space itself moves. The ship sits inside a bubble of flat, ordinary space. Around that bubble, space-time is contracted in front of the ship and expanded behind it. It's not the ship crossing the universe. It's the universe being reshaped around a stationary ship, like a surfer sitting still while the wave carries him forward. And this is a loophole. Einstein's speed limit only applies to objects moving through space. It says nothing about how fast space itself can expand or contract. The ship stays still relative to its own little bubble. So, technically, no law of physics is broken. This isn't even a new idea in principle. The universe itself expanded faster than light just after the Big Bang. Alcubierre essentially asked, what if we could do that on purpose in a controlled pocket of space? So, how do you actually bend space like this? You need something physics doesn't hand out easily, negative energy density. This isn't just less energy. It's a theoretical state where energy density itself is less than zero, a real, if extreme, concept in quantum field theory. We've actually glimpsed hints of it in something called the Casimir Effect, where two metal plates placed extremely close together experience a measurable negative pressure from quantum vacuum fluctuations. To generate the negative energy density needed at the scale of a warp bubble, the math calls for a substance nobody has ever isolated: exotic matter. It's not alien metal. It's a theoretical form of matter with negative mass energy, and it's the single biggest missing ingredient in this entire theory. Now here's where the video earns its title, because the Alcubierre Drive has two problems that keep physicists up at night. Problem 1, energy. The original 1994 calculations suggested you'd need an amount of energy equivalent to the mass of an entire planet, Jupiter, in some estimates. That's not a fuel problem. That's a we'd need to consume a planet problem. But here's the progress. In the 2010s, NASA physicist Harold White proposed reshaping the bubble, thinning it, changing its geometry, and the energy requirement dropped dramatically. We're talking a reduction from planetary mass down to something closer to the mass of a spacecraft itself. That's the difference between physically impossible and absurdly, but not infinitely difficult. It's why this research didn't die in the 90s. It's why NASA's Eagle Works Lab actually spent time studying it. Problem 2 is worse, and it's the one most videos skip: Hawking radiation. As the bubble moves, particles from a vacuum get trapped and accelerated at its leading edge, building up into a wall of extremely high-energy radiation. If you ever try to stop the bubble, arrive at your destination, that accumulated energy would slam into everything in front of the ship. In plain terms, the front of a warp bubble might act like a blowtorch aimed at whatever you're trying to reach. So no, we're not building a warp drive next year. Maybe not this century. But the Alcubierre metric matters because it proves something important. Faster-than-light travel isn't automatically illegal under physics. It's engineering impossible with what we currently have, which is a very different problem. That distinction is why serious physicists keep coming back to this equation instead of dismissing it as fantasy. The Alcubierre Drive is a perfect example of something I love covering on this channel. Ideas sitting right on the edge between science fiction and real, testable physics. If this kind of breakdown to real how, not just a wow, is what you're here for, hit subscribe. I'm covering topics exactly like this every week on MrAITech, and you won't want to miss what's next.